Okay, let us start with a quick recap of what we did last time. So, we were looking at a system which is described by the following classical action. Okay, and then you have a psi star minus h hat psi. Okay, and if you take this action and write down the Euler-Lagrange equations, you will get the Schrodinger equation. Okay, and then for this infinite dimensional system, it's infinite dimensional because you have a field rather than fixed number of coordinates here. We could do the following. We could expand psi as x. Okay, that's what we did, where the UNs are the eigenfunctions of this Hamiltonian of the single particle wave, single particle quantum theory. Okay, this one. Okay, so let me write that down also. So h hat, don't need, let's not write a hat here, it's h psi is, sorry, what I want to write is this h operator acting on un gives you En un. Okay, so these UNs are eigenfunctions of this operator h. Okay, so we did this expansion and then we took the a's as the generalized coordinates. Okay, and found out that the corresponding conjugate momenta are IH bar, A star, T. Okay, so that's what we found. And then we said, okay, we want to make a quantum theory out of this classical theory. So I will replace the coordinates in this theory, the a's, let me write here, and the a's and the p's. Okay, I'll replace them from being functions to operators and impose commutation relation. Okay, so if I do that, we saw that we get, let me put a hat now because I am saying these are operators. Okay, and if I impose the commutation relation, then this is IH bar. Okay, and sorry, it's better to put it like M here. This is M. So you have delta Mn. Okay, and we saw that this leads to the following: An hat T, Am dagger T. Okay, so An hat and Am dagger, they give you delta Mn. So that's the commutation relation between Am and Am dagger. Okay, and then we constructed the Hamiltonian for this theory. Let me remove the timeline. Okay, anyway, so I do not recall how to remove this lower part. Okay, so if you construct the Hamiltonian of this theory, this quantum theory, it turns out to be the following. Okay, which is really a sum of infinite number of harmonic oscillators. Okay, so our system has so the description of this system is, this quantum system is that of infinite number of harmonic oscillators. harmonic oscillators. Okay, and these oscillators have different frequencies. So the frequencies are omega n is En over h bar. Okay, where h bar is the Planck's constant. And also from the Hamiltonian, it's clear that these different oscillators, they are not interacting with each other. Okay, even though the h hat here or the h here has a potential, it has a V in it, as you saw last time. But anyway, after quantizing, this system becomes that of harmonic oscillators which do not interact, and there are infinite of them because the summation runs from 1 to infinity. Okay. So to proceed further, it will be useful to recollect what you already know about harmonic oscillators. So that's what I'm going to do. So a brief recollection of that. Single harmonic oscillator. Oh, I see. Okay, let's recall what we know already. So I believe that you have already learned this. So you know that for a simple harmonic oscillator, the Hamiltonian is h bar omega a dagger a, okay, plus half h bar omega. Okay, that's the Hamiltonian for the harmonic oscillator. So right now I'm looking at one harmonic oscillator. So if you want to drop this term, what we can say is, let's say I'm not interested in this term, so I subtract out from the Hamiltonian this ground state energy, because this is the one which gives you the ground state energy. So I will remove that part, okay, and I will just take the Hamiltonian to be h bar omega a dagger a. I can do this here, there is no problem. Okay. Now you define a state ket 0 by saying that this state is such that if you take the operator a and act on this, then it annihilates it. Okay, that's the definition of the ket 0. Okay, this ground state, this ket 0. And then you may ask, what's the, is it an eigen state of the Hamiltonian? So let's see. Let's ask, what's this? For a moment, I will keep this entire full Hamiltonian here with the 0 point term also. So I have h bar omega. Sorry, I'm sorry, this is not, I'm asking about Hamiltonian acting on this. Okay, so you have h bar omega a dagger a acting on this, okay, plus half h bar omega acting on this, okay, because it has two pieces. So what you get here is this a acting on the ket 0 will kill this state, okay, this ket 0. That's how it has been defined. So this piece goes away, and what you are left with is half h bar omega ket 0. So clearly this state ket 0 is an eigenstate of the Hamiltonian with energy half h bar omega. Okay, if it is an eigenstate, the eigenvalue is energy. So that's the energy of this ground state, this state, and you already know it's a ground state. And then you also recall how to build up states in this theory. Okay, you operate with a dagger acting on ket 0. Okay, and let me give an example of this. So you ask what this is, and you can start trying to figure that out by operating with the Hamiltonian on this state. Okay, because maybe it's an eigenstate of the Hamiltonian, and it is. So you have, okay, now I'm going to drop the this term, okay, half h bar omega I'm not going to carry anymore. So you have half, h bar omega a dagger a, and then you have this piece A dagger ket 0. Okay. So what is this? This is h bar omega A dagger, that's fine. Now if you could bring this guy, this A, next to the ket 0, next to the vacuum, then it will annihilate it, right? So that's what I'm trying to do. But for doing that, I have to use commutation relations. Okay. So the commutation relation between A and A dagger, and A dagger is 1. So I will have, let me look at this piece. So this piece I will write in the bracket, or let's write a round bracket. It will give you A dagger A plus 1 acting on ket 0. Okay. Now when this operator acts on this ket 0, it kills it. Okay. So that term is gone. You are left with only this. So you are left with h bar omega A dagger ket 0. Okay. Now this A dagger ket 0 is what you started with. So clearly the A dagger ket 0, this state is an eigenstate of the Hamiltonian with energy this much. Okay, and you already know that if I act with a string of A daggers on the ket 0, okay, I go up the ladder and they all are eigenstates. Okay, so if you take A dagger twice, okay, and ask what's the energy of that state, you will find 2h bar omega. Right. So that's something I believe is familiar to you. Now we can use the same thing in our present context, because our system is after all a sum of lots of harmonic oscillators and they are not talking to each other. So this formulation, this method will work. So what we do is we define a ket zeros. Okay, define a ket 0 to be that state which is annihilated by every n. Okay, so this is 0 for all n. So it's annihilated by A1, A2, A3, all of them. Okay, let's see. Okay, and of course you can see that your h acting on ket 0. Now h is the Hamiltonian corresponding to infinite number of oscillators. This will also be 0. Okay, because your h contains an A on the right hand side, and that A, there is a summation over of course n, but A n is going to annihilate it. So that's why you get this. Okay. Now let's do the same thing as we did for single harmonic oscillator. So we take a state A n, let me write it m just for ease, and act on, so this is m, and A m dagger ket 0, and ask is it an eigenstate of the Hamiltonian, and that's easy. So you have summation over n h bar omega A n dagger A n, and then we have A m dagger ket 0, right. So you have summation over n h bar omega A n dagger. Now if I could take this A n to next to the vacuum here, that will kill it as you saw before, and that's what we want. So let's do it, but this time it's not just 1, but you have a delta function. So you have to put a delta m n ket 0. Okay, if you recall the commutation relation, I think we can go back a few here. Okay, that's good. So now this annihilates the vacuum, so this term I can forget, The only term which is relevant now is this one. Now this delta mn will force the n here to become m, okay, and the summation will go away. So only that term is picked up. You get a m dagger get 0, and of course you have an h bar omega. Okay, so you see that this state is an eigenstate of the Hamiltonian with energy h bar omega. Okay, so if you excite any of the harmonic oscillators to the first excited state, that state where one oscillator is excited is an eigenstate of the Hamiltonian of your theory. Okay, that's what it means. How about this? Okay, maybe I should go to the next page. Okay. How about this? So I start with a n1, a n2. Okay, instead of m and n, I am writing n1 and n2. Okay, that's maybe there is no need to do that for now. So let's write a m a s, okay, and we have two daggers get 0. Okay, and ask whether this is an eigenstate of the Hamiltonian, and if so, what's the energy of this state. Okay, so I will put h bar omega a n dagger a n here, and there is a summation over n. So what does that become? Okay, I have been missing the n's here. Okay, there should be an m. There should have been an n. Okay, that's fine. Omega n, and you have a n dagger. Now I want to take it through this string. Okay, so I can just give you the answer. This is a simple exercise you can do. You have to just use the commutation relation, and you will get the following. Okay, you will get this, that this state is an eigenstate. So you will get a m dagger a s dagger acting on ket 0 again. Okay, that's something which is going to happen. And then you have h bar omega m plus h bar omega s. Okay, so it will be just the sum of these two energies. Okay, so that is another thing. I will give you one small exercise to do. Check whether, let's say, a n1, a n2, a n3, this one, whether this one is an eigenstate of the Hamiltonian. Okay, so I have not put a dagger here. I have put the daggers on these two, but not on this one. Whether this is an eigenstate of state of the Hamiltonian. Okay, so at least we have an understanding of this system, what it looks like, how to construct states of this. Okay, what I will next do is try to show you that this system which we have is equivalent to another system, okay, which will be the first which will be a first quantized theory. So this is a second quantized theory because you have done two quantizations. One you have started already with Schrodinger equation, and then on the top of it you have quantized A's. So I will take this system and show that it is equivalent to another first quantized system, and then I will make some remarks about why this description is useful. Okay, and after I have done that, I will leave this description and we will start doing quantum field theory for Klein-Gordon fields. Okay, so I have started this this description using Schrodinger equation because this is a familiar equation and one can immediately jump into the field theory by quantizing something which we all already know about. Okay, so let's meet in the next video.